or they as part of some other things we will explain, are a solution to the phase ordering problem. So here's some code, right? We take our one and we write it somewhere in memory, we read something back and add and blah, blah, blah. We read at some unknown address based on some variable we haven't computed that way. Let's optimize this code. So we can do store to load forwarding, where if we write somewhere and then immediately afterward, or really any time before having overwritten that location, read it back, then we could just like avoid the round trip and just use the thing directly. So we can replace the mem0 in the second line with just a 1. Okay. But now we can see that 1 plus 2, like I don't need a computer to compute that. At runtime, I can already do it when compiling the code. So we can constant fold this addition to a 3. And since A, like having a is equal to 3 is never used, is not useful. But A is only used here. So we can like just put the 3 where the A is. And when we do that, we realize that we have written somewhere and then read it back. And we did not know of this in this first step, since we hadn't figured out the address at which we will read. But now, once we have figured it out, now it's possible to do the same store to load forwarding. And then we have the same scenario again, where we get the 9. And this is optimized. So this example illustrates that when optimizing code, it's not a question of taking every optimization that we support and doing all of them once, but rather, depending on the program structure, we may need to run optimizations multiple times in some specific interleaving. So it's like more complicated than one might initially think. Here is another example where our program is x times 2 divided by 2. And we can optimize this, but here we can actually optimize it in 2 different ways. So, and this is like the A corresponds to this node, which can be optimized in different ways. So if we take the multiplication by 2 and replace it with a left shift by 1, so this is thinking about the number as a binary number and adding a 0 at the end. So that's multiplying by 2. That's equivalent. And like maybe for some part of our architecture, it is possible to compute. So this is an optimization. But this is also an optimization. So we could reassociate, we could like use normal rewrite of like think real numbers, let's ignore overflow and stuff. And we can write it like this instead. And this computation is not like maybe beneficial, like it still does the multiplication, still a division. Maybe this is not a faster program. But it's a different way of rewriting it. And realizing that, oh, we can reassociate, maybe we can't realize, like we have our theory of multiplication and division, but if we introduce a left shift, then that theory doesn't work. So like it's an exclusive choice of going to this or this. But then once we have reached this state, we can like realize that 2 over 2, that's just a 1, and multiplying by 1, that's the identity. So we can further optimize this down to just x. And I think everyone agrees that x is a better program than like any expression in x. So we have this thing, which is better. But like it wasn't obvious that we would take this path. We could have taken this path. And in fact, if you sit at A and you do the like locally optimal thing, if you only look at how much does this optimization improve the program, then you would end up at B, not at C, which ends up in the right location. So this is another complexity. It's not just having to do optimizations multiple times in some weird order, but also like, how do you choose what optimization to make? So in a traditional compiler, which is what we have described here, like first applying this optimization, then this optimization, if possible. Then we like walk along a path of this is the program, and hopefully we end up with something which is better. But in reality, we have seen that the world looks more like this, right? There are many choices. You may branch, you may like have things that end up joining again. Colors here would illustrate different kinds of optimizations, and the key point is just that there are lots of colors, and colors may occur many times or multiple times along a path or whatever. And the problems that we saw was that we have branches, so the order in which we apply optimizations matters, as well as we have to do local choices. So that means that whether, like, when deciding whether to go here or here, we can't know like the fact that we can't know the future if proceeding along this path. You could address both of these with some like recursive backtracking search thing where you go here and then if you decide that, oh, I'm not happy with this choice, then let's go back. But then like that would be very slow. And then the third problem is the fact that this space is huge. Like actually, like, yeah, there are so many different ways of expressing the same computation that yeah, it's like even if you have some, you would need Oracle to find the right path because you can't visit all the nodes. And this that we saw is just not a theoretical problem, but rather a practical problem, and like a quite significant practical problem as such, because we don't just have 3 different kinds of optimizations, we have lots and lots of optimizations. And this means that you will like never find a globally optimal program, but like maybe that's not the actual goal. But rather the other problems are magnified. So if it takes some time to run each pass and you have 100 passes or even more, then that takes a lot of time. And even figuring out as a compiler developer in what order to run the passes, and like if some pass need to be run multiple times, then you need to figure that out and like hard code it into your compiler. And this is like a real mess to handle as a compiler developer. And one solution to this, which will lead us into eGraphs, is instead doing equality saturation. So this is the same graph as before, but we have the perspective shift of rather than seeing this as one program that will then transform and like get another program, what this actually means is that we have identified multiple programs that actually are equal. So we have some space of many different possible programs, and they're all equal. So what we can do is that we can try to build this space in some sense, and then pick the right solution. And if we were to do this, we would not have the order dependency problem because we would like take both choices whenever we have the possibility of making a choice. And that eliminates both order dependency and like not seeing into the future. But the obvious problem with this approach is that this space is absolutely enormous. So it's like not viable to like take whatever memory usage your compiler is already using and multiply it by an exponentially large one. That's not viable. So the solution to this is that eGraphs are a way of representing this space of programs. So we will motivate this by thinking about how can we, given some program, like compress it or represent it in a compact manner. So the most like simple way of representing some program, like we have talked about computed programs, and we will now talk about mathematical expressions. There is a correspondence there, and there are multiple ways, and we will not go into how to represent programs as referentially transparent expression soups. Okay, so expression tree, like we have A and B, and we do this addition, and we feed it like this. A computation such as A plus B could be computed once and stored, but in a tree representation, we can't capture that. So we have this obvious duplication of these substructures. And that makes it very natural to talk about DAGs instead, so directed acyclic graphs, which are very close to what we just had. This is the expression DAG, and this is the tree and the DAG for the same program, the one we saw previously. And you can think about this deduplication as whenever you have some sub-expression which is syntactically identical, we can merge those. And you could call it common sub-expression elimination in a compiler setting. And a DAG is more compact, but a DAG still has duplication. If we have these two programs, and they are like different programs, right? One is doing like call is XOR, but it could be any operator really. Addition. So these are different programs. But when storing both, we kind of need to store them separately. All of the common inputs can be deduplicated, but like common outputs, like common ways of processing different inputs cannot be deduplicate. So like all of this storage is unnecessary. And egress are a solution to this, and we have some like funny boxes and circles that we will talk about very shortly. But the key part of egraphs is that previously we did syntactic merge. So whenever sub-expressions were exactly syntactically identical, we can just refer to them again. Egraphs track what computations or like what sub expressions, what their like values are. So that in the case of these different ways of computing stuff that are then used identically, then we do the deduplication. So we like only have like adding the XOR is just adding one node rather than adding a bunch of nodes. So we can think about this as an extension of the DAG in that we now do a semantic merge. And this is very nice because when doing program optimization, we are talking about taking some small part of the program and replacing it with some other program that computes the same thing. And computing the same thing means that we can use like without knowing, like it's possible to do deduplication of this structure even when these are not different. It's much more complicated. So we can exploit the fact that when doing optimization, we will have the fact that we will maintain equality during the rewriting, and that allows us to do this very natural representation of our programs. So what does this actually mean? So the split is splitting our computations, our circles that were fed into other circles. We split into computations and values. So every computation has a value or belongs to a value. We can have multiple computations computing the same value. So therefore, we let computations be circles that sit within boxes. But then whenever we like feed inputs to our computations, we don't care about how those inputs were computed. So we feed values. So edges go from boxes to circles. So if you squint, like if every circle is the only circle in the box, then it's basically the same as the DAG previously. But now when adding another way of computing something that already exists, we just add a computation, we don't add any value, and we don't disturb anything that uses the thing we just changed. Okay, so let's now use egraphs for quality saturation, which means that we take our egraph and we like mutate it over time. And the nice things about mutating egraphs is that rather than a program that you rewrite and you forget what you have previously, you only ever add the things to the data structure. And also all of the like adding this and adding that is the same as adding that and then adding this. All of the mutations on an egraph are commutative, which kind of corresponds to the not forgetting property. So this is an egraph where x times 2 divided by 2 is the program, same as we saw previously. We have drawn it slightly differently. So instead of circles sitting within boxes, we have circles pointing to boxes, and some box could have multiple circles pointing into it. That's just a way to make the drawing more skilled. Okay, so this is the program we saw previously. But now we do strength reduction, right? The thing we did when we illustrated how there's split, how there's like having to do local decisions is a bad idea because you don't know what's globally optimal. So we don't disturb anything of like the top of the tree. We add the 1, right? As a constant, as a unique value, because we don't have the value 1 yet. And we add a computation to an existing value. And that's all, right? So it's a small change to capture like this larger rewrite to the program, previously resulted in having to duplicate the entire program. Now we have a different rewrite, which is the reassociation, right? Doing the changing the parentheses. And now we change some more things because we like changed both the leaf and the root node of the initial expression. We like touch both the end and the start. But we have this new addition where 2 is divided by 2 itself, giving a 1. We don't know it's giving a 1 actually, so like these are different still, but that will soon change. And then the x is multiplied through with the 1 to give the ampersand. But then we do the constant folding of the 2 divided by 2, and we get 1. But 1, like on a syntactic level, already exists in our E graph. So we realize that, oh, this value we created previously as the result of this division already exists. So these are the same node. So let's add the merge edge, right? These are the same, but right now they weren't the same because we happened to draw them like before realizing that. And similarly, given that we now know that these are the same, that this is 1, then we can realize when looking at this, that multiplying by 1, that's identity, that doesn't change things, so we just keep these. And that allows us to realize that we should merge x value and the top value. So we have described this as adding edges, and that makes it easy to see that it's commutative to add this an edge or this edge. It doesn't matter which order you add edges. But actually, like given that these are the same, we could just contract this edge. So let's do that with both of the dashed edges that denote values being the same. And we get this graph, which is a little bit more messy in that, like the green now illustrates that 2 divided by 2 is a 1, and 1 times an x is still an x. And if you like did this contraction earlier, then you would like have a smaller E graph while processing it. The merging serves to make the graph smaller. And it's an important part of how you use them to do variance analysis. So how do we do like all this entire process I described with a bunch of drawings? How do you do this in practice? So in practice, you have theory languages, which we describe here. So we have like 3 blocks. We have some kind of theory schema. We have a bunch of rewrite rules, and we have something we do with the theory. So in the schema, we declare the symbols we have and like the general structure of how things work. It's like the generate data type. I mean, it says data type in this declaration. And then we have rewrite rules, which like somewhat magically finds, oh, if this thing exists, then we put this into the graph and say that this entire thing is equal to what we just had, which is like precisely how you kind of want to do rewrites. And we could like declare a variable x, like build our expression by combining the various nodes and data structure, and we can step a few times. Every step is like 1 round of trying to use the rewrite rules. Like if this exists, then put this. And since we do multiple steps, or at least black to green to blue to purple is multiple steps, then we need to do multiple steps in the computation to do this. But then once we have done this, if we ask what is the nicest way to write E, we will be told that X is the nicest way to write or compute E. And from a user perspective, this is kind of all you need to know. Well, not really, because you need to reason about the performance. But from a user perspective, this is what E-graphs are and equality saturation. It's like you write this program and it will just magically find everything that you can figure out based on these rewrite rules. And it does so by building this thing according to the rewrite rules. So previously we had already seen how equality saturation solves 2 of the issues, but it does not handle the exponential possibilities. And E-graphs don't, like, fundamentally, it seems impossible to solve, like having exponential growth at all. But this E-graph is way more compact than representing each of these 5 programs separately, and the speed up is even greater proportionally for like larger programs. So E-graphs actually make equality saturation kind of viable, which is very nice because we love to not have to deal with those 2 problems, which are such a pain for compiler writers. And at the same time, this is very nice to work with, and it like gives this formal interpretation of our things. Like this is algebra basically, which means that writing one rewrite rule for an optimization is way nicer than writing some ad hoc compiler pass. So this also makes it like a secondary effect on being able to reason and prototype your compiler. Another question is, how do you implement it?
Yes. I didn't say this. Okay, so we have some pattern, and we want to we have some sort of database of terms, and we want to find. So yeah, we alternate between finding this pattern in the database, and we construct a giant delta of all the insertions we want to make, and then we insert all of them. So there are multiple ways to do to search for a given pattern. One way is to just do e-matching, but so we like iterate for every add, we iterate every possible null that could fit and every other possible null that could fit here. And then we get O of n squared because we sort of do filtering way later.
This left thing is like a natural way of doing the loops, because if you recursively walk your tree pattern, you will get this sort of structure.
So the optimal thing would be to do some early exit checks and do some more indexing. So finding this optimal loop structure is actually the same problem as query planning in databases.
In a relational database.
Yes, so this here is actually a semi-join, and this is actually an index filter, and we don't need to do some extra filtering at the end. Since we do it right here. And so the original query is just kind of this join.
What is a join?
Yes.
I have no idea. There's enlightened.
So a join is that we have some columns, and we want to find all the pairs of rows where this column matches. One way to do this is to iterate all pairs, but then we get back to like this very slow thing. So we when we want to care about performance, we introduce indexes. So we have in the add relation, we create a map. So for a given x, we can find the entire row. So when we iterate through all of our multiplications, we can just immediately find the correct add. When viewing through the database perspective, we can do another optimization called semi-naive evaluation. Since we constantly add new information to the egraph or the database, we know that all the joins that only include all the information is already done. So we can think about what we add to the database as a delta. So delta null is what we added to the database. So the null and add here are the part that actually already part of the database. We know that this join has already occurred. So whatever information we get from this is already part of the database. So we therefore only perform the joins that or we can split up our join into the pairs with all the combinations of old and new. And so we only need to do these 3 joins, which seems like more work because we're doing more joins, but this is way less information, and it becomes this is very beneficial when our delta is pretty small. Right. History.
So we talked about motivating e-graphs, how e-graphs work, and how you implement those. And we kind of glossed over who invented what here. So e-graphs are in some sense quite old, but they were not used for equality saturation until 2009, which is semi-recently. But then there were still some things making them slower. So this batched phase, rather than being more eager in when you mutate the e-graph, was introduced by in 2021. And then in 2023, we have this whole thing with semi-naive join and relational tables, allowing loop flexibility for planning for optimal loop ordering.
Yeah, it's notable that Oatlog is both the an engine that implements Oatlog and also the language Oatlog. So we also implement Oatlog.
And that very naturally brings us to what we have done for this half year. We have implemented Oatlog, and Oatlog is an egraph engine, and it's compatible with Oatlog the language, and it's supposed to be faster than Oatlog the engine, and it's to some extent both of these.
Yeah. So what do we actually do? Well, we at compile time, you provide some schema and rework rules, and we emit a ton of code, and this is thousands of lines. And so we essentially like at compile time create an egraph engine that's like specific to whatever rewrite rules you have and whatever schema you have. Yeah, so correctness. We seem to be doing the same thing as Egglog. So the way we test Oatlog is just like we compare what Egglog does. And quite a lot of the tests in Egglog have like some surface level front-end features that we're missing, but we don't really care about those. For like all the tests that like run fine, we are correct.
And like adding support to those 63 extra tests is like, it's a matter of adding things that kind of have places where, oh, this is how you would implement it. It's not conceptually difficult to implement.
Yeah, we can
almost all of it.
Quite a lot of them you can just like edit the test slightly and it's like it's compatible.
And then there are some which, yeah, let's not talk about.
Yeah, and we also do like snapshot testing for the like generated code and other IRs, and we also do property testing of our indexes. Yeah, results.
We are really, really fast. So this is a large table, but it's like actually I think easier to read than a figure. Like 3 benchmarks: fueled, math, and Boolean adder. Like they are like reasonable benchmarks where you like do lots of algebraic manipulation basically. This is the key column, which is E nodes. It's the size of the E graph that we build. So this ranges from, so the way we did the math is we like added some things to the thing and a bunch of rewrite rules, and then we like step through it. And in every step it grows. Math actually grows infinitely because it tries to solve integrals by partial integration arbitrarily deep, which doesn't converge.
Math is the same benchmark as Egglog uses, so we're not like cheating by using benchmarks that are made for our engine.
Yes. And so like for very small E-graphs where you just have like a few hundred nodes, we have like 50 times speed of like wild numbers. And then for like larger numbers, like depending on use case, you would like fall into different places in the range. We still have range speed ups.
So this in gigabytes is.
Yes, so like this is 15 million E nodes, and this is using 4 or 5 gigs of memory. This is 25 million E nodes, and this is using like 50 to 60 gigs of memory. So like it's not really like we stopped benchmarking when we had worse numbers. It's the fact that scaling beyond this is like
we're not like super sure what happens, but like we're at the point where like we're running around for RAM anyway, so we don't really care too much about that.
And like even if the speed up is like 2 times at a large E graph, that's still quite nice. And like here it's a bit lower, but it's still not slower than Egglog, which is the like other like I mean you saw the 2023 timestamp, right? It's like the mainstream fastest engine.
Right, demo. So there's a cool fractal called the manifold set, and we want to do it quickly. So there's this formula, and there, but we use like 7 operations, and that's too much. CPUs can do fuse, multiply, add, and you just like with magic you can do A plus B times C. So we want to like find this optimally, and we can do it with Oatlog. So here we have the like theory language, and we have some extra commutations for fuse, multiply, add. So we like represent it explicitly.
And there are multiple of them because you like negate input. So
we have like kind of obvious rules and whatever for. I'm not sure if this was like strictly needed, but the like commutativity is needed probably, and we have some lowerings too. So whenever we see something that could be a fuse, multiply, add, we say this is equal to doing a fuse, multiply, add.
Can you zoom in?
Yeah, so they're like relevant. I don't know if the names make they're like. I think this is like about as good as Intel does with their like intrinsic names, but so yeah, if we see something that is like we take A plus B times C, we say this is equal to a fuse, multiply, add.
Like when building a theory, you could like think about what exactly are the rules I need for my thing, or where you can just like take some repository of like, oh, this is Boolean algebra or whatever.
Yeah.
And like both methods work on load and method, maybe you still work for the
Yes. The interface is like some like not
we have
so
not prioritized the interface.
Yeah.
So we have some macros here that we're applying.
Yeah, so you have like instead of having a name for a variable, you have like variable ID 0 to 3, and this is like the computation we're doing. And in a loop, we apply our rules once and then canonicalize, and then we try to do an extraction of both of the expressions that we care about. And if we run this, I only print when we get the new ones. So in the beginning, we have like essentially the original expression with like var2 being CR. And at the end, we get like a fused multiply and a multiply and fused multiply, fused multiply. So yeah, we like basically get this at the end. So we can open up to questions or whatever.
Do we have opposition during the room? Yeah,
We have more slides on implementation if you want to ask about that.
okay, please, go ahead.
Okay, so then like show what goes around like small examples, like how like feasible be to use egress for like larger programs.
There is a project called eggcc, which essentially is an optimizing compiler, and it has like thousands of rewrite rules, and it's used for Egglog. And since we basically support what the Egglog does, we can do basically the same thing.
Yeah, so like with slight modifications, we can run their so Egglog is the interpreter, we are a compiler, which means that the way that HCC interfaces with Egglog is by generating a theory file, and like the top of it is just some rewrite rule. There are lots of rewrite rules, but that's fine. And then there are like 20,000 lines of global variables in the theory, corresponding to your program that you're compiling. So I guess like mostly for that reason, and that's we code in that with the Rust code that like will at startup do all of the inserting your entire program into the egraph. Like this is like if you want to feed a bunch of data, you don't do it by generating Rust code and then feeding it to Rust C, which takes forever. So compiling this thing takes.
It takes 20 minutes and crashes Rust C unless you like give it more stack space.
Yes, but you could like look, yeah.
But if you like feed it like in a reasonable way, I don't think that would be an issue.
Yeah. So like the other question is like, are egraphs useful at all? Like our project isn't using egraphs to make something useful. Other people are doing that, and like they have some success.
All right. Can you express all kinds of optimizations that compilers need with egraphs, or what are the kinds of optimizations you can't if there are?
So we can like with like relational queries, you can you're like basically as powerful as a data log, but with equalities. So you can say if these things exist with these constraints, then insert this. But you can't say if these things exist and not these other things. Or like you could add something like that. But yeah, I think the main limitation are like inlining and like.
So like the thing we saw was a rewrite rule. Here's a pattern, right? That's like syntactic. Look for this syntax, replace with this syntax, and claim that they are the same, and then let the egraph do whatever it will with information that they are the same. You could like add to this a little bit, and this is also made possible with the database representation, although we like to go into it here. And you can also add various guards to, well, you can only do this syntactic rewrite if this like semantic criteria holds, and you can do like some.
The like typical example is you can like reassociate if you're not going to divide it by 0.
Yeah. Yeah, but like you're limited to having a tree input, tree output. So inlining.
Well,
like, stuff that moves an arbitrarily large number of nodes.
Yeah. Well, if you have like well, we can add more things. We like have a tiny graph, a fixed graph becomes another fixed graph. But yeah.
It's possible to extend the graph in some very specific way.
Yeah. So I have like some question about like top fair event happenings. Because you're doing like a lot of ahead of time of your Oatlog. So is it a fair question when you
So we select our indexes ahead of time, but we don't actually like construct the graph ahead of time. So like we can see like the schema, but we are like we don't do anything with the actual input.
So in like this example, basically our program looks at this section of the program and like does some fancy global reasoning things, kind of. But this part is left unchanged. And even this is like the Oatlog way of doing it. If you actually were to use Morphing in a compiler, you would probably feed this data to it at runtime, as we do in the demo.
But like we're not like saying that Oatlog is bad. It's like a really useful tool, and actually it being dynamic is very useful.
If you're hacking on your rerun rules and like are they correct, have I like made things unsound?
Yeah. But if you have like a fixed set of rules, then you're fine with like paying a like extra
10
compiler.
second or something.
Yeah.
Extra cost.
What was your hypothesis on improving on Oatlog? What was, did you see that the ahead of time would improve, and did you get those wishes?
Yeah.
So like, this is super surprising, and we
like we haven't really talked about how, like, why are we faster? So it's like a mix of things. Honestly, we don't really know. We have like some guesses. We have some new techniques, some optimizations on the theory that are made possible by knowing the entire theory ahead of time. You could like remove some rewrite rules because they're implied by others and some stuff like that. And then it's just like lots of constant factor and doing profiling and like, oh, can I prefetch this value? Well, in the end, without the prefetching, it wasn't useful. But yeah.
What was the initial idea that we could build a better Oatlog?
well, we like read that Oatlog was an interpreter, and we wanted to do ahead of time and just assume that like it would be enough to make it faster.
It's
But-
also just the fact that like Oatlog was published 2023, and that was 2 years ago, and like it's not like obviously there are things that you could improve upon that people haven't already realized.
Yeah, we
And then like maybe we expected that we would reach parity and that stuff. Like that's could be another outcome. The fact that we have such large speedups is not what we anticipated.
yeah, like Oatlog is still quite high performance because it's like written by actual database researchers.
So what were the benefits of implementing Oatlog as like procedural macros in Rust instead of other approaches? What limitations is it?
In terms of like in practice, it could be a command line tool that outputs your Rust code and you commit. Well, like I don't know, if you want to generate code in Rust, like a proc macro is kind of the way to do it. The idea with like having it be a proc macro and not actually more standalone build script would be the Rust term for it. Is that we thought we could, if you want to like interleave, if you want to have primitive functions, like you have booleans and integers in our Oatlog code, but maybe you want your own Rust types, then it's like quite nice to embed like interleave Rust and your own macro.
Right now you can kind of add primitive functions if you want, but it's like
That's extremely hacky.
yeah.
In practice, we don't use this, but the reasoning was, well, maybe let's do like more primitives and like interacting with the sounding application. Although what we like to do, also we didn't expect, this is another thing, to be like actually implementing Oatlog. We thought we would like do kind of Oatlog, but not be compatible. But then we realized that if we can be compatible, then people will care much more about our work. So we did for not strict compatibility in terms of all features, but strict compatibility in the sense that you could add all of the extra features.
Right. What are in this evaluation? Do you know how many rewrite rules you have per these examples?
You can
What can you?
I think math has maybe math has maybe 15, 20 or something, and Boolean is more, but also there are probably redundant rules in Boolean.
Yeah, Boolean was like I looked on the internet of like what are all the Boolean laws and just added all of them. So it's like it's a very bad benchmark actually. So
Math is more interesting, I think. So the Boolean adder instantiates the like Boolean circuit of a 10-bit adder, like a ripple carry adder, and then it just explodes. Because there are lots of ways to express 10-bit Boolean addition. This is math. Math is more interesting. Like we have sure addition is commutative, and then the way the thing it actually solves is mostly like it computes some integrals.
like if we remove this rule, it will be way faster because like this is the one that actually makes everything explode.
So the integral laws are like not very interesting. Like cosinus can be integrated to the sine, and like it's linear adding subtracting or whatever. But we do integration by parts in this long rule, and like I don't know, if you like taken a course in analysis, you may have like tried to do integration by parts, you realize that it doesn't work, and you might have given up. This program just like but if 1,000 iterations integration by parts didn't work, we do 1,001 instead, and that just doesn't work. It gives like lots of fun math for our engine to shoot through, but it doesn't really useful. So actually, some of our benchmarks were called fueled math, which is this thing that we restrict the number of nestings of integration parts. To actually solve these integrals, I think you need maybe 1 or 2 levels of nesting.
But so the comparison you had was these 25 rules that we
Yeah. So we have seen this is like integration by parts stuff, and then the Boolean adder is a 10-bit Boolean adder, as you would implement it like hardware ripple carry adder. And if you go to the benchmarks. Yeah, so this is the math benchmark in like many more steps. So in like step 12 of math, then I think it would actually do 12 nested integration by parts, so it's huge.
We get like basically a times 10 increase. So like we don't have a chance of like we need to buy a lot of RAM to.
And Boolean adder is like similar. I think this multiplication is by is it?
Like this is since like
It's kind of by 30 or 40. It grows extremely quickly between these two. And then these fueled math are math running all the way to saturating the V-graph. So actually like computing the entire V-graph. And it's not all very large because we limited the amount of nested integration by parts.
The point of having the fuel benchmark is that we want to like to like make a fair benchmark where we like modify how the rules work. Then we need like some like goal to reach, and a reasonable goal is just like until we can no longer apply any rules.
Yes. If you actually were to use Oatlog for a real thing, like sure this is a nice speed up, but I think actually you will get even larger speed ups. So we have 2 modes, strict and relaxed, in terms of how closely our implementation or like some kind of less interesting semantics of the E-graph, like the ordering of in which things are numbered. Okay, so basically relaxed mode is used for the fueled ones, and that gives like a 30% speed up or something. By realizing that if you have a commutative relation like addition, if we know that 1 + 2 is 3, we also know that 2 + 1 is 3. So we can like this kind of half our work, both in terms of storage and compute in a relaxed mode.
You made a lot of professional tag. What are there any other egress engines?
Not really. Or like there are a lot of egraph engines that act like egg, but there are not a lot of egraph engines that act like Egglog.
The core of egg is like a few hundred lines of code. Everyone who acts on egraphs adapts to egg basically. Egg is not relational database. Egglog is relational database. Egglog is like, I don't know, 10 times faster than egg. Something, it's way faster.
And you can like get arbitrarily faster by just having complicated queries.
Because egg did the thing where it just puts the for loops when it's recursion, but puts the for loops in this order. While Egglog actually takes a bit about in this order to put the for loops.
So egg is actually fine if your queries are quite small.
Yeah, so like comparing to egg would just give even larger speedups. Also, to compare it to egg, we would need to like rewrite all of our theories into egg, which is like difficult.
Yeah,
We implement the same language as Oatlog, so it's natural to compare to Oatlog. It's also possible to compare to datalog engines. These are basically like logic programming language relational databases, but they don't do the quality things of the graphs.
the thing that makes us very different from a datalog engine, kind of like in computations, is that when we like merge two e-classes, we actually need to like modify our database. But in datalog, you can always everything.
Remember the fact.
Yeah,
So-
you never modify the history, but we kind of need to modify the history.
Yes.
We can put it in it's actually in both slides. Like
Yeah,
kind of-
my
yeah.
point was that, like in datalog, you could implement a thing like this, where you would like explicitly represent equality edges, but that would like grow more, and like you would often have, basically this would grow faster. So this is what a datalog engine would do, and a like more native egraph engine would do this. So like it's unfair, but presumably, like I don't think our performance is like magical. I think you could maybe get on par with us in like by using one of the mainstream datalog engines because they have received lots of focus. But we can do things that they semantically in the same language.
If you just like, I've like skimmed some datalog implementations, and they seem to be doing basically the same thing, because like both Egglog and datalog are like, they're like part of the same research community basically.
And also some of our optimizations are egraph specific. They use the semantics of how groups work.
All right, thank you. We will send the other parts on text, and they're
Okay.
small, but otherwise I had another small question here on the tree expression and expression tree and expression DAG. Isn't tree a DAG, or is it common to separate?
Well,
I mean, a tree is a DAG, but a DAG is a more general structure.
like if you're in Haskell, you can't tell the difference.
Sure, you can say that this is a DAG, and both of them are graphs, but like, what was the difference? The difference is that one is a tree and one is not a tree.
Yeah.
I agree, this is like not a big like. Basically, like if your compiler has this, it also has this. This is mostly to illustrate like syntactic merge and then semantic merge. Like this is not a great insight. It's like everyone, this is obvious like to everyone writing these sorts of things.
Thank you.
Implementations.
Like questions or we
Yes.
have extra page.
So like stupid layman question, but like, okay, so just the thing Oatlog does, so in summary, the Oatlog finds the same optimizations as Egglog. It's just that it takes less time between you clicking the compile button and your compiler.
Yeah, like we have two. If we made a compiler with Egglog and Oatlog, the compiler made with Oatlog would just be faster, but produce the exact same binary, basically.
And then I talked like a little bit about the strict versus relaxed mode of Egglog. If we took the math benchmark and we enabled the relaxed mode of Egglog,
Oatlog.
these numbers would increase faster. So you would reach saturation earlier. And it means that running relaxed mode is like way more work than doing strict mode 12 steps, because strict mode 12 steps doesn't realize many things.
Yes, so when you've actually like saturated the graph or like sufficiently far, and you actually want to select a kind of representation of the thing, the expression you're optimizing, how do you select?
It's a very simple NP hard problem.
Yeah.
So what you do in practice is that one thing you can do, if you want to print it as an expression tree and want to minimize the size of that, then it turns out it's just like polynomial thing. Or like
linear time
yeah.
dynamic.
And there are like some heuristics you can do, and there's like a cheating way you can do it by saying that like if the egraph has a bounded tree width, which is some like random property that says like how close is it to a tree, and if it's like kind of close to a tree, then you can do it in fixed parameter linear time, but like, so yeah, extraction is hard, but
In practice, you either like imagine that you will be extracting a tree, although you will be extracting a DAG, and under the assumptions you're extracting a tree, you can do linear time dynamic programming. That's what everyone like. That's also what Oatlog does, like by default when you use it interactively.
but like
and-
even if you can't do perfect extraction, if we like can equate a bunch of things, we can still screen the program and improve things, even if like.
Yeah. So growing the E-graph and extracting are kind of different problems. And then if you have a small E-graph, you can do integer linear programming. I think in practice as well, people do. Maybe people do the weird tree-wood thing.
Let's take one more question. This is a really short one. You said it, I just didn't parse it. How much RAM did you say that huge number was?
This is 5 gigs, this is 50 gigs, or maybe 60.
And you needed to buy more RAM, why?
Or like
No, no.
if we were to run
There
for
you have
another
128.
No. By like that's not an option. I don't know. Boolean adder 13 is probably absolutely enormous. I have no idea how much it is. Math 13 steps, I did get it to run yesterday. It used like 80 gigs or something. And that was like when running it standalone, but then I like enabled it in the benchmark suite and I ran the benchmark suite and I disabled the log for the 13 steps because that wouldn't work. And then it's somehow out of memory. So I just decided to not add them 14 because like even then you probably don't get it.
Okay. So let's thank the presenters again. And I think we can conclude now. So remember to send me email after this presentation and send to ask me for signatures. And if you're not in the audience also, but as an opponent, please write that down so that I will sign the correct field. Okay, thank you.
Bonus slides.
Yeah. Okay, architecture, whatever, yes.
So I have some comments on the very of the architect. So if you please come to my office when you're done here. So next group is coming in at 5 minutes. So you know where my office is. So it's 512. Just follow me and I will give you the
Yep.
Thank you, everybody in Slack and Zoom.